Okay, thank you. I'm going to talk a bit about PDB-REDO Cloud, and it's all about structural biology and reproducibility. Hang on. Okay, so imagine that you're doing a structural biology study, and you typically use experimental structure models. And depending on the type of research you do, you have data sets of different scales. So your typical biology or biochemistry analysis of a specific protein or a complex is just 1 to 10 structures. But if you do drug discovery or you do any sort of study that involves homology, this rapidly scales up to tens or thousands of structures. And that means that you cannot really look at these structures by hand anymore. If you do method development for crystallography, or you're doing data mining to find out structure parameters for validation, this scales up even bigger to almost 10,000 structures. And particularly when you do AI approaches like AlphaFold, you just want to get as much data as you can possibly get, and this can be hundreds of thousands of structures or whatever you can get at that point. Now, the key data source for these sort of data sets would be the protein data bank. And it's been a great success for more than 50 years now. But it also has some drawbacks. So the entries in the protein data bank are created by different people at different times. So people have done different things to their experimental data to make a model. And the entries in the PDB are almost never updated in terms of the structure itself. So the structure models are done with methods that are not up to date. And in terms of model interpretation, quite a lot of these models have errors or problems that can actually be solved. And this is why we created PDB-REDO as an alternative data source. So what we do is we take the PDB model and the original experimental X-ray data to update these PDB entries with the latest crystallographic methods that we developed and other people have developed as well. So the procedure is you take the model and the data, and there's an extensive parameter optimization to refine the model. We do some model rebuilding, some more refinement, and a structure analysis that includes a lot of model validation. And this procedure is fully automated, so that adds consistency to your data set, which is very useful. And it's applied to all the models in the PDB. So what comes out is a data bank with models that are generally improved in terms of model quality and have fewer errors. And here you see an example below. If you look at the PDB model here on the left, you can see that there's a UDP binding site that looks all right, but is quite a bit off when you look at this phenylalanine in the top left corner. In the PDB-REDO model, you can see that both the UDP and the binding site have slightly changed, but in a way that it explains the biology much better. Now you can see that with this new conformation of this phenylalanine, you can see that the UDP base is stacked between two aromatic residues. So if you're doing a study on ligand binding, this is a much more useful data set. So nevertheless, PDB-REDO has its own problems as a data source because it's a living data bank. It changes a lot. So if there's a new PDB entry, obviously there's also a new PDB-REDO entry being made, so the data bank grows all the time. And this is hundreds of entries per week. But if a PDB entry is changed in terms of annotation or otherwise, also the PDB-REDO entries get replaced. And this is tens of entries per week. But every once in a while, there's a big change in annotation, and there's large batches of entries that are then replaced. And because it's still under active development, we still come up with new algorithms, and we then apply them to all the PDB-REDO entries that are relevant. So those are replaced as well. So if you do a study based on a data set from PDB-REDO, all of a sudden your original data can be lost. So that is a problem for scientific reproducibility. And that encouraged us to do this project here. So we had 4 challenges. First of all, we wanted to make the PDB-REDO data bank much more fair than it already was. And we wanted to improve provenance tracking of PDB-REDO entries. So make sure that it's very clear where they come from. But for reproducibility, the most important thing is that we don't throw away models that people have used in their studies. We make sure that they're available so that people don't have to keep a copy themselves, but they can just point back to it. And finally, we wanted to make sure that the data bank is much more searchable, so people can create data sets for their structural studies much more easily. So what we've done is that we made the PDB-REDO data bank much more fair. We did a lot of integrity checks. We cleaned up all the legacy data, but more importantly, we replaced all the data that was in proprietary data formats. For instance, we had a lot of ligand validation information and ligand interaction data, like I showed you the example before. And that was just in a completely unminable plain text format. So this is now cast into a JSON data set. But JSON data, even though it's structured, it's completely useless if you don't have a description of that. So we added JSON schemas that describe what the data actually means, but it can also be used for validation of the integrity of the data. Next step that we did is we extended the provenance tracking of PDB-REDO entries quite a bit. So originally, essentially, it was just the PDB-REDO entry of PDB entry 1 ABC. But now we actually document which version of the original PDB coordinates we use, which version revision, and also of the experimental data. So it's much more precise in where it points to. But we also keep track of the things that we've done to the data. So every once in a while, you need to do manual edits because of limitations of our own software or because of the model annotation. And even though we do these things by hand, this is automatically captured in the procedure. So this is tracked. And the PDB-REDO pipeline consists of quite a lot of programs, more than 60 at this point. And all these programs have impact on the outcome. So you need to keep track of all the versions of all the programs that are used. So you can also completely redo the calculation if you have to. And all this information is captured in the file called versions.json, again, with a JSON schema attached to it. But we also keep procedural data. So if you run PDB-REDO with non-standard settings, this is also captured. So completely reproducible now, hopefully. In terms of not deleting old entries, we implemented a sort of rollover system. So PDB-REDO entries are rolled over rather than overwritten. And essentially, that means that for every entry linked to a PDB entry, there's an attic that has all the previous versions available. And we keep the final structure model, the final electron density map, and this versions.json that describes how the model was made. But we also keep a lot of other metadata. So the procedural data, but also crystallographic parameters and all the validation data that we have that comes out of the PDB-REDO calculation. And these are stored in a file called data.json. Now, each version in this attic has a unique 9-character persistent identifier that is based on the checksum of versions just JSON, so it's unique, but it's also persistent, and I think that's the most important thing. Now, this rollover procedure is built into the main PDB-REDO pipeline, and that's just to avoid any accidents. Right, so you cannot accidentally overwrite things if you do something on a different computer and then copy things over. It's all part of the main pipeline. So and the attic versions are made immediately when a new entry is made. So everything is consistent and hopefully robust. Another thing that we did is that sometimes PDB entries are obsoleted for various reasons, and which would also lead to the obsolescence of a PDB-REDO entry. But here again, we keep the attic, so all the previous versions are remain available and reproducible. Now, what we still have to do is make these attic entries directly accessible through the PDB-REDO website. They're available through the data bank, but not through a graphical user interface yet. So finally, in terms of data bank searching, we've indexed all these data.json and versions.json files, put them in a PostgreSQL database, and this is done now automatically with every update of the PDB-REDO data bank. And we made a search API that takes queries in JSON format. It will be a full REST API at a later stage. And these queries can be combined as consecutive filters to build up your data set. So here's an example. Let's say I want to do machine learning on protein structures that have or need peptide flips. So in this query, we take only the latest PDB-REDO entries, and we do filters on more modern PDB-REDO versions, so greater than equal than version 7.21. And we take all the entries that have at least one peptide flip. And even though these names sound a bit abstract, these are all documented in these JSON schemas. So these can be automatically visualized as well, what the things mean. So the return would then be a list of entries with their version hash, and you can add this as supplemental data to your publication. So you point to your exact data sets rather than an abstract description in your methods section. This already works, but we're implementing a graphical user interface to build up these queries in a more user-friendly way. So what is the impact of this research on the different infrastructures? So I think our main user base is in the Instruct and Elixir community. And we have, of course, an overlap with the user base of PDB-E, and we collaborate a lot with them. So there's data exchange between us and them in both directions. And the databanks are part of a network of interactions in structural biology. For instance, we use PDB-REDO to annotate AlphaFold models from AlphaFold-DB, and this is done in a thing called AlphaFill, and this is directly connected to the user community, but this also goes through the PDB-E knowledge base. So there's all sorts of different networks within these research infrastructures that benefit from this project that we've done here. In terms of the impact on EOSC at large, I think we've brought access to the PDB-REDO structural data bank to a new level of sophistication, and more importantly, a new level of reproducibility for structural biology research in EOSC, but also outside of EOSC. And our experience of working within the EOSC-LIFE and the technical teams was pretty good. We were very happy with the outreach from different packages. We were also particularly happy with the FAIR hackathon. That was very informative, and we learned quite a few new things there. In terms of future work, we still need to work on documenting the API to make access more easily. We are always interested in connecting the PDB-REDO data to other resources, and we do this through, for instance, 3D beacons, but we'll be extending that even more. And I think the major impact always comes from users. So we do a lot of outreach to reach the widest possible audience. And I think sustainability is very well covered. Everything is implemented in such a way that it's fully automated. So there's very little maintenance requirements. Nevertheless, it's good to know that the main developers are on permanent contracts, so the manpower to maintain things stays available. And this is important for any new development. And it's fully embedded in the PDB-REDO research line. So also keeping this going is just part of the normal funding cycle of the research. So with that, I want to extend my thanks to particularly the developers at EBI and PDB-E, but also at the Instruct EOS team. And with that, I'd like to thank you for your attention.
Wonderful. Thank you very much, Robbie. So lots of interesting things there. We've got a couple of questions. So Petter, would you like to go first?
Yeah, thanks. That's related to the work we're doing in the work package 6 of EOSC-LIFE on the provenance, because your work very much fits on what we're doing there. And I wonder if we can actually make an experiment where we would turn the PDB-REDO provenance into, or put it onto the common provenance model, embedded basically on it.
We can have a look at that. That sounds interesting.
Thank you. So the next question is from Henning, and I'm not sure if Henning, because he's not a panelist, I'm not sure if he can speak, so maybe I'll ask it for him. It says, Robbie, are you providing information on how much entries have changed or whether they have changed between versions? And he has no idea how you could quantify it, but it's like a quantifiable diff between your entries, I think.
Yeah, so this is essentially a query that you can do. You can you could, I'm not sure that you can do it in a single query, to be honest, but you can definitely do it in two. So you can see which new attic entries are spawned within two versions of any program, for instance, the full PDB-REDO pipeline, and then you can see how many entries have changed between versions. So yes, you can do this sort of queries, and the idea is that we index all our metadata, so you can make very complicated queries if you want to, including these.
Right, thank you very much. I had a question as well for you. So you talked about your alpha fill, and I was wondering, because you are effectively providing a kind of a more curated and quality improved data set, if you fed that into AlphaFold, whether you think you would get better predicted structures out of the other end rather than retrofitting it onto their existing predictions. And if you did that, how would you test it?
Well, it's the retrofitting is of course of ligands, which AlphaFold doesn't do at all.
Okay.
Right? So it's different. So it's enriching the AlphaFold models. It's not changing them, right? In terms of the protein. This is always hard to prove. So because machine learning has such, particularly deep learning, has lots of layers of abstraction. Yes, I would think it's would lead to improvements. But if these improvements are meaningful at the level of precision of AlphaFold, I don't know. We've seen examples where there's clear errors in AlphaFold, but I think most of them are just error margins, and the problem lies in the interpretation. But we can see in ligand binding sites, particularly that there's parts of AlphaFold that are brilliant. They predict ligand binding site perfectly, even though the ligand is not there. But with metal binding sites, we also see that that's not always the case. And yeah, perhaps they could have learned a bit from PDB-REDO. It's hard to tell. Okay. Nobody wants to repeat that calculation.
No, well, nobody probably can afford to repeat that calculation. But yeah, interesting. Thank you very much. I really like this model of improving the provenance and then feeding it back. I think it's really, really powerful. And then the other question I had was, given that you're kind of stacking up version history, for quite a large data set, I wonder if you get into cost questions of how much data you could afford to store over time as this runs, because it does start to cost money to store repeated versions. Is your compression good enough?
That is a risk. We had a look at it. It seems that every time we keep a new version of a PDB-REDO entry, it adds about 10% more storage, because we keep only the final things that you really need for provenance, not the intermediate things, and it compresses quite well. So nevertheless, this will lead to an increase, but I think storage costs at the moment still go down faster than that our data grows. So for the time being, we're not too worried about that.
So
but
when
yes,
Moore's law stops to apply, then you've got a problem, right?
Yeah, but Moore's law doesn't directly apply to storage costs, so that's a good thing.
All right. So that's really helpful. I think, we're looking at challenges of putting some things in cold storage just to reduce, some things will go to tape perhaps, as opposed to being live. Do you think that's a reasonable solution in this space for your versions?
Yes, eventually, yes, that would change the workflow a bit. So that might affect the robustness of it. But I can imagine that at some point, if you have a stack of 20 versions, you don't necessarily need to keep the oldest ones readily available. So moving to cold storage would be a solution then. But at the moment, the data bank is 1.9 terabytes, so it's not a concern yet.
Okay, brilliant. Thank you very much. That was a really powerful presentation. All right, so we're going